Greetings, calculus students. So we're starting a new section, a new learning target in calculus, and this learning target is called optimization. So optimization is a common word in the English language, and to optimize just means to make optimal, to make it the best possible situation. And so anytime you see something, words, so superlatives is the English word for it, but like biggest, smallest, cheapest, strongest, ugliest, those are things you're trying to optimize, okay? So optimize can mean the biggest or the smallest. It asks this question, what's keeping us from making something infinitely big? So for instance, if I want the biggest, couldn't I just say, well, make it to infinity? In the real world, we know that there's always some limiting factor or constraint that prevents that from happening. So for instance, let's say I wanted to optimize my paycheck. Then I would just make it as big as I wanted. My paycheck is $10 million. However, there is a constraint in that the school cannot pay me $10 million. So I would say, I want to optimize my paycheck. I want to maximize my paycheck based on the school budget. Or another example in the real world, I might say I want to minimize the time each day I spend working. I cannot, in the real world, spend just 0 hours working. That would be totally minimizing it, 0 hours of work per day. So a constraint I might put is, what is the minimal amount that I can work, but still be a good teacher to my AP Calculus students. And so now that minimum is at least 8 hours a day. If I worked less than that, I wouldn't be the best teacher. So anyway, we are going to be learning to optimize things in the real world. So these types of problems are your favorite problems. These are our awesome word problems. Yes, kind of like related rates were word problems. But these are word problems where we're going to be optimizing or finding the extreme values of things. So that word extreme should be familiar. What we're going to be doing, I'm going to write a subtitle up here, is we're finding the absolute extrema. But this is the word problem edition. Okay, so in our previous unit, we had a lot of experience finding absolute extrema or relative extrema. Now we're doing it, but in the context of a real world situation. Cool. So we're going to start off with not really the most real world. This is definitely more of a math situation. But with example 1, we're looking for two numbers whose sum is 60, and whose product of 1 times the square of the other is a maximum. So just like we did with related rates, let's start by labeling our variables and then writing what we know and what we want. So if I have two numbers whose sum is 60, I'm just going to let, so this is what I know. I'm just going to let x be one number, and I'll let y be another number. Doesn't really matter. I just have two numbers. And then I also know the sum of them is equal to 60. Cool? And then what do I want? I want the product of 1 times the square of the other. So 1 times the square of the other is a maximum. So I'm going to call this is the product. So the product is 1 times the square of the other. 1 isn't referring to the number 1, it's referring to one of the numbers. Okay. So if we think back to our process for solving like maximum extrema problems, like when we were solving these, what we would do is we would find our max and min by finding critical values, right? And these critical values where f prime equals 0 or f prime does not exist, right? And then we would solve for x. And that's what we're doing here. So if I want, if I want to find the largest product, the maximum product, that's what I'm maximizing. I'm maximizing P, okay? So I'm gonna add that to my want to maximize P. So whatever it is we're trying to maximize, that's what we're gonna take the derivative in terms of. I see that I have two variables over here, x and y. Before I take the derivative in an optimization problem, I need to reduce this to just one variable. So that's kind of a difference from related rates. In related rates, I was usually given enough information that I could still have two variables because we were using implicit differentiation, and so we ended up getting like dx dx or dx dt or dy dt. But in this case, we don't want that. We want to be able to substitute back in. And so that's where this other equation is going to come in. This is what is known as a secondary equation. And this secondary equation will help us create, it's kind of like creating a system of equations so that I can write an equation just in terms of one variable. And so the way I'm going to do that is I'm going to solve for x. And then I can plug this value of x into my primary equation that I want to maximize. So I will replace 60 minus y with x, and then y squared equals p. Okay. Before I take the derivative, I'll simplify this a little bit more just by distributing y squared. And now I can go ahead and take my derivative. Since I just have my p, that will just become p prime. I do not have to use implicit differentiation because I only have one variable. So I can just do the regular derivative, 120y minus 3y squared. And now I'm going to set that equal to 0 and solve. So I'm setting the derivative equal to 0 to find my critical value. So let's factor this thing. I can factor out 3y from both terms, and I get 40 minus y equal, well, never mind, getting rid of that part. And then, so I can, now that it's factored, I can set each of these terms equal to 0 to solve for y. I get y equals 0 and y equals 40. So at this case, I kind of need to think about the domain that I have. I can't have y values less than 0. Essentially, the domain here is 0 to 60, since 60 is my maximum number. And so since this one, y equals 0, is on an endpoint, I'm not going to include that one. So my y value is going to be 40. The question is asking for the two numbers, so that means I don't just have to solve for y, I need to solve for x as well. So over here, I can plug in my y, and I get x equals 60 minus 40, so x equals 20. So these are my two solutions right here. They both add up, their sum is 60, and then the product of one of them times the other one, so y is the one that I'm getting squared, is the maximum product there. Okay. All right, let's flip the page to some more examples. Okay, so example 2, let's say I have 8 inches of pipe cleaner. So that's just like a bendable piece of fabric that you can bend into shapes. So you can see on the right, this picture, that pipe cleaner was bent into a little human. And let's say we want to form this into a rectangle, okay? So here's our rectangle that we made using the pipe cleaner, the 8 inches of pipe cleaner. We can just label our sides. I like to label x and y based on its orientation. One thing that I know is since I only have 8 inches of pipe cleaner, I basically know that the perimeter of this rectangle, so 2x plus 2y, is going to equal 8. So this is all the stuff that I know. And that's about it. But the question is asking what dimensions of the rectangle will produce the rectangle with a maximum area. So I want to maximize the area. So that is what I'm eventually going to take the derivative of. So the area is x times y. I'm going to have to use my secondary equation over here. So this is my secondary. To plug into my want equation so that I only have one variable. So that means I need to solve for either x or y. It doesn't really matter. Make your choice. Sometimes it will make the problem easier or harder based on which one you decide to simplify. In this case, they look really similar. So I'll just solve for x. So I get 8 minus 2y equals 2x, and then divide by 2, 4 minus y equals x. So that's what I'm going to plug in up here. 4 minus y for x, then I still have times y. I'm going to simplify this by distributing the y. And now I'm ready to take my derivative. I'm going to maximize it. So I'm going to take the derivative, and to find my critical values, set it equal to 0. So I get 4 equals 2y, so y equals 2. Then I'll find my x by plugging in 2 for y. And so I find that x equals 2 as well. So usually when we're maximizing rectangles, the maximum area for a rectangle is always going to be a square. So when it has equal sides, that is going to maximize the area of a rectangle. Cool. Because this is a real world problem that has my units, I do want to include units, and those were inches. So x equals 2 inches and y equals 2 inches. Okay. Before you move on, always make sure to just reread the question to make sure you found what you needed. This says what dimensions of the rectangle will produce the rectangle with the maximum area. I have my dimensions. Sometimes the problem will say, and now find the area, and so I'd have to find the area by multiplying them together. This case I didn't, so I'm done. Okay. Example 3. A ladybug farmer has 500 inches of fencing and wants to fence off a rectangular field that borders on a straight river. Okay, let's draw this so far. So I have a river. I'll make it blue, highlight it. So here's my river. That's yellow. Sorry for that squeaky noise. I didn't mean to do that to your ears. Okay, here's my river. Woohoo. Trying to do it as straight as possible. And then my fence. And I don't need to draw the fence along the river because the river's kind of acting like the other side of the fence. Okay, so it says he needs no fence along the river. Be careful for those details. You don't want to draw the fourth side when you don't actually need it. I was also given, well, I'll label these. So y, y, and x. And I was given that there's 500 inches of fencing. So the amount of fence that I have is 500. Oopsies, 500. And that's going to equal the perimeter. So that's 2y plus x. So this is everything I'm given. This looks like my little secondary equation right there. The question says, what are the dimensions of the field that has the largest grazing area for his hungry ladybugs? So want to maximize area again. Okay. So even though I'm missing that fourth side, the area of this thing will still be x times y, length times width. And I'm going to solve for my secondary equation. It looks like it's a little easier to solve for x. I will just subtract 2y. And that's what I'm plugging into my area equation. Cool. So this follows very similar steps to the last problem. So I kind of want you to try to solve this on your own. I will look to see whether you solved it on your own. The answer that you should get by the end, just so you can check yourself, is y equals 125 inches and x equals 250 inches. Okay, so that's how you can check yourself at the end. All right. Example 4. So another ladybug farmer, or the same ladybug farmer, has purchased some expensive, extraordinary diva ladybugs. So these are some fine-looking ladybugs right here. Ooh, cute. Okay. And so these ladybugs need more space. They want exactly 10,000 square inches of grazing in order to be their optimal ladybug-like state. Okay, so they just want more space. What is the least amount of fencing required to get the diva ladybugs at their optimal state if the farmer is still allowed to build along a very straight river? Okay. So we're going to have our same river, and then the fence. Oopsies. My fence like this. Y, X. But this time, instead of given the amount of fencing, I was told the area. So my secondary equation is that x times y, the area, equals 10,000. Okay? This is what I've been given. And I want the least amount of fencing. So I want to minimize fencing. And usually we want to minimize when we want to save money. So I want the most amount of area, but I want to use less fencing because I want to spend less money on it. Fencing costs money. So the equation for the fencing is the same as it was up there. You see I have 2 y fences plus 1 x. I need to use my secondary equation to get rid of one of those variables. We've been solving for x the whole time. Let's solve for y this time. So y equals 10,000 divided by x. So we can take this and substitute it in up there. So I'm going to get f equals 2 times 10,000 over x plus x. This well, now I have to multiply 10,000 times 2, but whatever. So f equals 20,000 over x plus x. That's as simple as this is going to get, so let's take the derivative, f prime. This derivative, you can kind of imagine that this is x to the negative 1. Right, I could rewrite this as 20,000 x to the negative 1. So then the derivative, I'd bring down the 1 times 20,000. And then the exponent would become x to the negative 2. So that is x squared, like that. Right? And then this derivative is just 1. Okay? I'm going to set this equal to 0 and try to solve for x. So some of you might be panicking right now because we have this like x squared and we don't know how to factor it. But if we have one term with an x and the other with not an x, just put the term without the x over there, and then we can multiply by x squared to get rid of that ugly fraction. So then I get negative 2,000, or negative 20,000 equals negative x squared. If I have negatives on both sides, I can get rid of it by multiplying by negative 1 on both sides, and they'll just become positive. And then the square root. So x equals the square root of 20,000. What a mess. Okay. We might have to simplify this a little bit on the calculus exam, but we'll leave it like that for now. Let me look back. What was this question asking me? So what is the least amount of fencing required? So I don't even actually have to solve for y. some of your instincts based on what we did would be to plug this value of x in for y. And that's because all the other ones like asked for the dimensions. So it said, what are the dimensions, which would be to find x and y. But this is asking me for the amount of fencing. So I can actually just plug my x value into this equation right here. So plug it into that equation that just has x, and then I'll solve for f. So that's what I'm going to do. So f equals 20,000. My bad. I should have highlighted the other equation. This one's more simple. Whatever. So 20,000 divided by the square root of 20,000 plus the square root of 20,000. And this was in inches. So this is how much fencing I want. This is very exact. I don't think you could ever order this amount of fencing. They'd probably ask you to round to the nearest inch. But for the AP exam, we're going to be exact. There's our solution. Okay. We're going to do one more problem together. This is another mathy one, but we're going to update it a little bit because I didn't want to torture you. Because I'm nice, despite what some of you think. Okay, so let's update this. We're going to say find the point on the curve, and instead of being y to the x squared, we're going to turn it into y equals 4 minus x squared. It's easier, trust me. And then closest to the origin. Okay? So find the point on this curve, y equals 4 minus x squared, closest to the origin. So in order to understand what's happening, let's sketch this. So I have a parabola that's been shifted up 4, and I know that at -2 and 2, I have x-intercepts. So something like this is good. And I want to find where is it closest to the origin. Okay, so basically I'm looking for a point. I don't really know what that point is, so I'm just going to I'm going to choose kind of any point, and I'm going to call it xy. Okay, oh, I forgot, I wanted to add a domain restriction. So on the origin for x greater than 0. So there's my domain restriction. I only want for x greater than 0. So that's the right side. That's this side of my graph. Okay. So I'm just going to label this xy. I don't really know. I could have drawn the point anywhere else. Could have been xy there or xy there. It doesn't matter. But I'm just going to put it there, and I'm going to call it xy. And so closest means I'm trying to minimize the distance between the origin and the point xy. Okay, I'm going to minimize the distance between those 2 points. So distance between 2 points, you should kind of think of your Pythagorean theorem. So I'm trying to find my hypotenuse. So I'm going to write / hypotenuse. Okay, so the distance is the hypotenuse of this triangle that I can label, since my point is xy, I can label the side x, that side y, and I'll just call this d for distance. So the equation I want to minimize is d squared equals x squared plus y squared. And then my secondary equation is actually the equation I was given in the original word problem. You will pretty much always be given the secondary equation in the word problem. So I'm going to use that and plug it in here so that I only have one variable instead of 2. So 4 minus x squared squared. And then I do have to take the square root, like this. X squared plus 4 minus x squared squared. Okay. So one trick that I want to teach you is if you have something annoying like this where you need to minimize an equation that's a square root, we can make this a little bit simpler, and I think you'll like it. So I'm going to highlight that, and I'm going to say here's a trick. Okay, and so this is when you have a single radical. Single radical, single square root. Okay, so the trick is that minimizing the whole radical, or the whole radical is the same as minimizing the argument of the radical. Okay, so pause me and read that again. So if I just have the square root, what I really just have to simplify is the argument, which is this highlighted part inside of the square root. So that makes it so much easier because then I don't have to take the derivative of this big ugly square root. And so I'm going to keep writing in blue for the little trick, and I'm just going to recall this A, I guess, for argument. And so what I'm really just going to simplify is this thing. Like that. Then a little bit more simplification. A equals x to the 4th minus x squared plus 16. Cool. So that derivative now is so much easier. I don't have to worry about chain rule. I know you hate chain rule. Come on. And we don't have to worry about it. So I can just go a prime equals 4x cubed minus 2x. And then set this equal to 0. I'm kind of afraid I made a mistake, but I don't see one. So I guess I'm fine. Okay, so I can factor out 2x. And I'm left with 2x squared minus 1. And then I am left with x equals 0 and x equals the square root of 1/2, plus or minus the square root of 1/2. So let's remember my domain. My domain was for x greater than 0. So the only critical value that I'm going to keep is x equals positive square root of 1/2. That's my only good one. Okay. So that is the x value of the point. The question wanted the point, so a point consists of both an x and a y. So I will plug this back into my original secondary equation. That. So y equals 4 minus 1/2. Y equals, this is 8 over 2 minus 1/2, which is 7 over 2. So my coordinate point will be the square root of 1/2, comma 7/2. There's my answer. Okay, we're going to stop here for right now. The next video will be a lot more fun optimization problems.